years ago, about 9 years ago or so, they did a study at Harvard or one of the Ivy League universities, and it revealed that mathematicians looking at pictures of important equations or important derivations of theorems, etc., experience a reaction that is extremely similar to, if not identical, to the reaction experienced by artists or art lovers when they look at great pieces of art. And therefore, the study concluded that mathematics is objectively beautiful. I don't go for such things. However, it was instructive because apparently the first thing that intimidates people about calculus is the new symbols. The integral sign, the elongated Old Latin S, or the use of expressions such as these differential equations, etc. Things, in the 1800s, calculus was extended further into what's today called vector calculus, and that intimidated even the greatest of scientists and mathematicians via its introduction of new symbols. Michael Faraday, the great physicist, once even derided James Clerk Maxwell, one of the inventors of vector calculus, comparing these new symbols to the ancient Egyptian hieroglyphs, the carvings on the walls of the pyramids, in which each letter is a picture like a lion or a river flowing, all of those things. So the first thing that intimidates people is the introduction of these new symbols and these complex-looking expressions. However, the thing to remember is that the essence of calculus is not only independent of these symbols, but was invented or presented to the world completely without them. Because if you take a look at the Principia, the book at which Newton introduced what is today called calculus to the world, there is not one of these symbols present in its entirety. I can turn through the pages for you, and you can see that all you have is some of the images and figures and writing that you would see in your basic high school or pre-high school geometry, because that's all it was. The basic ideas of calculus, the essence, which is embodied in a couple of ideas, a couple of concepts, the concept of convergence, the concept embedded in the fundamental theorem of calculus. All of these are quite independent of the symbols you use. Not everyone shares that viewpoint, though, and that is actually the basis of the controversy, the historical controversy about who invented calculus, Newton or Leibniz, because Newton presented these basic ideas without any of the modern notation, and Leibniz invented most of the modern notation we use in calculus. And there is a body of thought among mathematicians and scientists that any new theory of mathematics is basically just a collection of new notations in which to express some ideas. It's an interesting opinion, it's an interesting way of looking at things, but not everyone agrees, least of all physicists. And if you don't agree, then Newton was the inventor of calculus. If you do sympathize with this idea that notation rules all, then Leibniz deserves more credit. In any case, what were these basic concepts which I referred to earlier? Hopefully you are aware by now that the word calculus in itself means very little. You have to usually attach it to something else for it to mean something, because calculus just means any collection of methods and concepts to aid in the calculation of something. It's basically any systematic science or any branch or collection of ideas in mathematics. So calculus of predicates, calculus of vectors, etc. And This, what we today is very simply just called calculus, should really, perhaps really be called the calculus of infinitesimals. So, what are infinitesimals? Well, infinitesimal, in a very important sense, is sort of a shorthand for infinitely small. So, we are concerned with infinitely small numbers, infinitely small sections of pictures, etc., etc., etc. And the reason that we're interested in the infinitely small is basically the exact same reason Newton was interested in it 300 years ago. And that is because at a certain scale, at a certain microscopically small scale, complicated objects become simpler to study. To wit, curved lines look like straight lines when you zoom in on any particular section of them. At least this is true of most curved lines. They have to meet certain conditions. And similarly, complicated variation, like, say, the blood sugar in a person's blood over time, can actually be studied as a quite a straightforward increase or decrease pattern if you restrict the time period in which you're studying it. So Newton was interested in this because he saw that the well-established geometry of straight lines and points established by Euclid some 2000 years before Newton was even born could be used or applied to the study of much more complicated things like curves which don't even have any name, like this one. And you could imagine these curves as being made up of a great many straight lines at a certain level. And indeed, those of you who have studied calculus in school or beyond school will probably have studied it in two sections, differential calculus and integral calculus. And though this division is mostly artificial, it's even more artificial after the invention of what's called complex analysis, it's a basically sensible division because it represents two different broad concerns, the local and what's called local and the global. When you zoom in on a complicated curved line and study the resulting straight line, you might be interested in answering a question like, in which direction was a car moving at so-and-so time during its journey? A question which can be answered if you simply zoom in on the part of the curved road on which it was traveling at the particular time concerned, and you see what you have is a straight line, which will tell you very clearly which direction in which the car was moving. It's very simply the direction in which the line extends. And you might be interested in something more obvious, like the length of this entire road, which winds like this in this complicated snake-like curve. In that case, you can simply imagine the curved line as being made up of these many tiny straight lines and add up the lengths of the straight lines. And usually this will result in a very simple formula. You can study what happens to the formula as the straight lines become smaller and smaller and smaller and completely merge into this curved line. So the first kind of problem is a local problem in which you're only interested in a tiny section, and it's generally what differential calculus deals with. And the second type of problem is a global problem, and it's what integral calculus deals with. And believe it or not, it's really as simple as that. There is just nothing more to it. Give or take a few details about straight lines that you perhaps are already aware of, are already familiar with. So what was the point of all this? What was the point of calculus ultimately? Well, in the first place, historically, Newton proposed the ideas of calculus in order to, in a sense, complete mathematics. He saw that the basic operations of geometry that had been used for 2000 years were extremely powerful, but they had to be supplemented. New ideas had to be added in order to correctly study nature, to study the much more complicated movements and behaviors of objects in nature. Well, nature is not full of straight lines and points that Euclidean geometry understands so well. It has curves and circles and parabolas and the like, and Newton found a way to study these things using the old Euclidean geometry plus a few basic ideas, the ideas we have discussed. In that sense, it is the most natural extension of Euclid's geometry. There's another deeper significance. You see, it was not simply that Newton had introduced ideas that allowed us to study the more complicated phenomena of nature than Euclid's geometry had allowed us before that. It was actually an expression of something deeply buried within our own minds. The idea that a curve can resemble a straight line when you zoom in on it is actually, as it turns out, deeply buried in our own psyche. It's really what allows us to understand intuitively what we mean to say that someone was running faster in the beginning of the race and slower near the end. The notions of calculus are, in a very important sense, an expression of notions we are born with, notions about speed and change and space and time. And the fact that Newton managed to put forth these notions as exactly as he did is really why he is revered the way he is today. You know, he's not just revered by scientists the world over, but there is a great incident described by the poet William Wordsworth, in which he describes having a sleepless night in some English town, perhaps it was Cambridge, and turning from his pillow and looking through the window and seeing in the moonlight the statue of Newton, and suddenly feeling extremely calm and extremely moved looking at that statue facing the night alone. And the concluding lines of the poem are truly a great tribute to the man, where he describes Newton's mind, a mind forever wandering the strange seas of thought, alone, which is a pretty great tribute and a pretty accurate reflection of Newton's contribution to mankind's body of thought and even the life of general society. Leo Tolstoy, in fact, makes use of the ideas of calculus near the end of War and Peace, sometimes regarded as the greatest novel in history. Tolstoy finishes the story by talking about what happens in the lives of some of the next generations of characters, and then he fills the last 100 or so pages of his book in detailed socio-political analysis. And take a look at what he says just about near the end, somewhere in the last 2 pages, where he puts forth his theory of how history should be studied, not as a series of great significant events involving great characters like a drama on a stage, but really as being made up of a lot of tiny dramas that lead to big events and big dramas. Let me read out exactly what he says. Here it is. He says, only by reducing this element of free will to the infinitesimal, that is, by representing it as an infinitely small quantity, can we convince ourselves of the absolute inaccessibility of causes. And then, instead of seeking causes, history will take the discovery of laws as its problem. The quest for these laws was begun long ago, and the new methods of thought which history must adopt are being worked out simultaneously with the destruction towards which the old history, perpetually dissecting and dividing the causes of phenomena is moving. And here he writes, all human sciences have followed the same path. Arriving at infinitesimals, mathematics, the most exact of the sciences, abandons this process of dissection and enters on a new process of integration of unknown infinitesimal quantities. Abandoning the concept of cause, mathematics seeks law, that is the property common to all unknown infinitely small elements. So, and then of course he talks about Newton a bunch of times near the end, but that's the point. The point is Newton struck on something deeply buried within us, and great thinkers like Tolstoy saw that it was indeed something completely human and completely natural to all of our thinking. So yeah, calculus has a point, and I hope we have some inkling of it now. Thanks for listening.